Traditional two-phase commit protocols block resources too long, violating availability requirements in high-volume FinTech systems. When transferring funds across decoupled microservices, like Account A Debit and Account B Credit, we face distributed failure without atomicity guarantees. A failed credit after a successful debit leaves the system inconsistent. The Saga pattern replaces atomic transactions with a sequence of local transactions, ensuring eventual consistency through the explicit compensation steps. This approach is mandatory when services cannot share a single database or transaction manager, which is standard practice in modern banking architectures. A Saga is fundamentally a sequence of local transactions, T1, T2, up to Tn. Each local transaction updates the database and publishes an event triggering the next step. If Ti fails, the Saga executes compensating transactions, Ci, Ci-1, up to C1, to undo the preceding successful steps. We implement orchestration, where a central service, the Transfer Orchestrator, manages the flow and state transitions. Choreography, relying solely on event chains, becomes unmanageable when compensation logic involves complex branching or external system calls, introducing significant operational complexity. The orchestrating service maintains the state machine for each transfer request. The core data structure, the transfer context, must persist the unique transaction ID, the current step index, the status of each local transaction, and necessary payload data like amounts and account identifiers. Persistence uses a transactional outbox pattern to ensure state updates and outgoing commands are atomic relative to the orchestrator's database. This prevents lost commands upon orchestrator failure, guaranteeing reliable command delivery to downstream services. The orchestrator sends a synchronous command, DebitAccount, including the transaction ID, source account, and amount, to the debit service. The debit service must implement strict idempotency checks using the transaction ID to prevent double debits if the command is retried. Upon successful debit, the service returns a 200 HTTP status and updates the local account balance. If the debit service returns a 4x error, the orchestrator immediately marks the Saga as failed and initiates the final notification step without compensation, as no state change occurred.
Following successful debit, the orchestrator publishes an asynchronous message, CreditAccount command, to a reliable message broker queue, such as Kafka or RabbitMQ. This decouples the orchestrator from the credit service availability. The credit service consumes this message, performs the credit operation, and publishes a credit completed event or credit failed event back to the broker, which the orchestrator subscribes to. Message delivery guarantees, specifically at least once delivery, necessitate idempotent processing on the credit service side to prevent duplicate credits. If the orchestrator receives a credit failed event, it transitions immediately to the compensation state. The first compensation step is invoking the ReverseDebit command, including the original transaction ID, source account, and amount. This command must verify that the original debit occurred and then increase the account balance. Crucially, the ReverseDebit operation must also be idempotent, ensuring that multiple compensation attempts do not overcredit the source account. The orchestrator waits for a ReverseDebit completed event before finalizing the Saga failure. Compensation for the credit step is only necessary if the credit service failed after processing the command but before confirming completion, or if a timeout occurred. If the credit service fails internally, it should attempt self-healing or publish the failure event. If the orchestrator times out waiting for the credit response, it must query the credit service state using the transaction ID before initiating compensation. If the query confirms credit occurred, no compensation is needed. If the query confirms failure, the debit compensation proceeds immediately. Once the Saga reaches a terminal state, either completed or aborted, the orchestrator publishes a transfer status event containing the transaction ID and final status details. The notification service subscribes exclusively to this event. This separation ensures that notification failures do not impact the core financial transaction integrity or block the orchestrator flow. The notification service handles user communication via email, SMS, or push, relying solely on the final status provided by the orchestrator for accurate reporting.
Tracking the flow requires consistent propagation of the transaction ID across all services and message headers. Distributed tracing tools, such as Jaeger or Zipkin, visualize the sequence of commands, events, and compensating actions, providing crucial insight into latency bottlenecks. Metrics must track the latency of each local transaction and the overall Saga completion rate. Specific alerts must be configured for Sagas stuck in intermediate states for longer than a defined threshold, indicating potential dead letter queue issues or service failures requiring manual intervention. The orchestrator must be horizontally scalable. Since it relies on persistent state, database connection pooling and optimized indexing on the transaction context table are essential for high throughput. Deploying the orchestrator using Kubernetes ensures automated failover and resilience. For operational stability, the orchestrator should implement retry logic with exponential backoff for transient failures, but only for idempotent steps. Non-idempotent steps, particularly compensation steps, require immediate failure logging or manual review initiation upon persistent failure.